Well, now that we've given you some power to make independent local state and to model objects, thought we'd do a bit of programming of a very complicated kind, just to illustrate what you can do with this sort of thing. I suppose, as I said, we were motivated by physical systems and the ways we like to think about physical systems, which is that there are these things that the world is made out of, and each of these things has particular independent local state, and therefore it is a thing. That's what makes it a thing. And then we're going to say that in the model in the world, we have a world and a model in our minds and in the computer of that world. And what I want to make is a correspondence between the objects in the world and the objects in the computer, the relationships between the objects in the world and the relationships between those same the model objects in the computer, and the functions that relate things in the world to the functions that relate things in the computer. This buys us modularity. If we really believe the world is like that, if it's made out of these little pieces, and of course we could arrange our world to be like that, we could only model those things that are like that, right? Then we can inherit the modularity in the world into our programming. That's why we would invent some of this object-oriented programming. Well, let's take the best kind of objects I know. They're completely wonderful. Electrical systems. Electrical systems really are the physicist's best objects. You see, over here I have some piece of machinery. Here's a piece of machinery. Okay? And it's got an electrical wire connecting one part of the machinery with another part of the machinery. And one of the wonderful properties of the electrical world is that I can say this is an object and this is an object, and the connection between them is clear. In principle, there's no connection that I didn't describe with these wires. I say if I have light bulbs, if I have a light bulb and a power supply is plugged into the outlet, then the connection is perfectly clear. There's no other connections that we know of. If I were to tie a knot in the wire that connects the light bulb to the power supply, the light remains lit up. It doesn't care. That the way the physics is arranged is such that the connection can be made abstract, at least for low frequencies and things like that. So in fact, we have captured all of the connections there really are. Well, let's even go one step further and talk about the most abstract types of electrical systems we have, digital circuits. And here there are certain kinds of objects. For example, in digital circuits, we have things like inverters. We have things like AND gates. We have things like OR gates. We connect them together by sort of wires which represent abstract signals. We don't even care as physical variables whether these are voltages or currents or some combination or anything like that, or water pressure. Okay? These abstract variables represent certain signals. Okay? And we build systems by wiring these things together with wires. So today what I'm going to show you right now, we're going to build up an embedded language in Lisp. Embedded in the same sense that Henderson's picture language was embedded, which is not the same sense as the language of pattern match and substitution was done yesterday. The pattern match substitution language was interpreted by a Lisp program. But the embedding of Henderson's program is that we just build up more and more procedures that encapsulate the structure we want. So for example, here, I'm going to have some various primitive kinds of objects, as you see. That one and that one. I'm going to use wires to combine them. The way I represent I can make wires. So let's say A is a wire, and B is a wire, and C is a wire, and D is a wire, and E is a wire, and S is a wire. Well, an OR gate that has both inputs, the inputs being A and B, and the output being wire D, you notate like this. An AND gate which has inputs A and B and outputs C, we notate like that. By making such a sequence of declarations, like this, I can wire together an arbitrary circuit. So I've just told you a set of primitives and means of combination for building digital circuits. Well, what I need more in a real language is abstraction. And so, for example, here I have a half adder. It's something you all know if you've done any digital design. It's used for adding numbers together on A and B and putting out a sum and a carry. And in fact, the wiring diagram is exactly what I told you. A half adder with things that come out of the box. You see the box, the boundary, the abstraction is always a box. And there are things that come out of it, A, B, S, and C. Those are the declared variables. The declared variables of a lambda expression, which is the one that defines half adder. And internal to that, I make up some more wires, D and E, which I'm going to use for the interconnect. Here E is this one, and D is this wire. The interconnect that doesn't come through the walls of the box. And wire things together, as you just saw. And the nice thing about this that I've just shown you is this language is hierarchical in the right way. If a language isn't hierarchical in the right way, if it turns out that a compound object doesn't look like a primitive, there's something wrong with the language. Right? At least the way I feel about that. So here we instead of starting with mathematical functions or things that compute mathematical functions, which is what we've been doing up till now, instead of starting with things that look like mathematical functions or compute such things, we're starting things with things that are electrical objects, and we build up more electrical objects. And the glue we're using is basically the Lisp structure, lambdas. Lambda is the ultimate glue, if you will. And of course, half adder itself can be used in a more complicated abstraction called a full adder, which in fact involves two half adders, as you see here, hooked together with some extra wires that you see here, S, C1, and C2, and an OR gate to manufacture a full adder, which takes a input number, another input number, a carry in, and produces output, a sum, and a carry out. And out of full adders, you can make real adder chains and big adders. Okay. So we have here a language so far that has primitives, means of combination, and means of abstraction. It's a real language. Now, how are we going to implement this? Well, let's do it easily. Let's look at the primitives. You see, the only problem is we have to implement the primitives. Nothing else has to be implemented, because we're picking up the means of combination and abstraction from Lisp. We're inheriting them in the embedding. Okay, so let's look at a particular primitive. An inverter is a nice one. Okay. Now, inverter has two wires coming in, an in and an out. Okay. And somehow, it's going to have to know what to do when a signal comes in. So somehow it's going to have to tell its input wire, and now we're going to talk about objects, and we're going to see this in a little more detail soon, but it's going to have to tell its input wire that when you change, tell me. So this object, the object which is the inverter, has to tell the object which is the input wire, hi, my name is George, and my job is to do something with results when you change. So when you change, you get a change, tell me about it, because I've got to do something with that. Okay, well, that's done down here by adding an action on the input wire called invert in, where invert in is defined over here to be a procedure of no arguments, which gets the logical knot of the signal on the input wire, and after some delay, which is the inverter delay, all these electrical objects have delays, okay, will do the following thing. Set the signal on the output wire to the new value. A very simple program. Now you have to imagine that the output wire has to be sensitive and know that when its signal changes, it may have to tell other guys, hey, wake up. My value has changed. So when you hook together an inverter with an AND gate or something like that, there has to be a lot of communication going on in order to make sure that the signal propagates right. And down here is nothing very exciting. This is just the definition of logical NOT for some particular representations of the logical values, 1 and 0 in this case. And we could look at things more complicated, like AND gates. AND gates take two inputs, A1 and A2 we'll call them, and produce an output. But the structure of the AND gate is identical to the one we just saw. There's one called an AND action procedure that's defined, which is the thing that gets called when an input is changed. And what it does, of course, is nothing more than compute the logical AND of the signals on the inputs, and after some delay, called the AND gate delay, calls this procedure, which sets a signal on the output to a new value. Now, how I implement these things is all wishful thinking. As you see here, I have an assignment operation. It's not set. It's a derived assignment operation in the same way we had functions that were derived from Carr and Kutter. Okay? So I, by convention, label that with an exclamation point. And over here, you see there's an add action, which is to inform the wire called A1 locally in this AND gate to call the AND action procedure when it gets changed, and the wire A2 to call the AND action procedure when it gets changed. It's all very simple. Well, let's talk a little bit about this communication that must occur between these various parts. Suppose, for example, I have a very simple circuit which contains an AND with wires A and B, and that connects through a wire called C to an inverter which has a wire output called D. What are the computations? Here's the physical world. It's an abstraction of the physical world. You know, I can buy these out of little pieces that you get at Radio Shack for a few cents. And there are boxes that act like this, which have little numbers on them like LS04 or something. Now, supposing I were to try to say what's the computational model. What is the thing that corresponds to that part of reality in the mind of us and in the computer? Okay. Well, I have to assign for every object in the world an object in the computer, and for every relationship in the world between them, a relationship in the computer. That's my goal. So let's do that. Well, I have some sort of thing called the signal A. This is A. It's a signal. And it's a cloudy thing like that. And I have another one down here, which we're going to call B. And it's another signal. Now this signal, these two signals are somehow going to have to hook together into a box, let's call it this, which is the AND gate action procedure. That's the AND gate's action procedure. And it's going to produce, well, it's going to interact with a signal object, which we call C, okay, a wire object, excuse me, we call C. And then this is going to put out again, or connect to, another action procedure, which is one associated with the inverter in the world, NOT. And I'm going to have another wire, which we'll call D. So here's my layout of stuff. Now we have to say what's inside them and what they have to know to compute. Well, every one of these wires has to know what the value of the signal that's on that wire is. So there's going to be some variable inside here. We'll call it signal. And he owns a value. Okay, so there must be some environment associated with this. And for each one of these, there must be an environment that binds signal. And there must be a signal here, therefore. And presumably signal is a value that's either 1 or 0. And signal. Okay. Now, we also have to have some list of people to inform if the signal here changes. Well, I'm going to have to inform this. So I've got that list. We'll call it the action procedures, AP. And it's presumably a list. But the first thing on the list in this case is this guy. And the action procedures of this one happens to have some list of stuff. There might be other people who are sharing A, who are looking at it. Okay? So there might be other guys on this list, like somebody over there that we don't know about. It's the other guy attached to A. Okay? And the action procedure here also has to point at that. List of action procedures. And of course, that means this one, its action procedures, has to point off to here. This is the things it has to inform. And this guy has some too. But I don't know what they are because I didn't draw it in my diagram. It's the things connected to D. Now, it's also the case that when the AND action procedure is awakened, saying one of the people who know that you've told, one of the people you've told to wake you up if their signal changes, okay, you have to be able to look and ask them what's their signal so you can do the AND and produce a signal for this one. Okay? So there has to be, for example, information here saying A1, my A1 is this guy, and my A2 is this guy. And not only that, when I do my AND, I'm going to have to tell this guy something. So I need an output. This guy. And similarly, this guy is going to have a thing called the input that he interrogates to find out what the value of the signal on the input is when the signal wakes up and says, I've changed, and sends a message this way saying, I've changed. This guy says, OK, what's your value now? Okay, and when he gets that value, then he's going to have to say, OK, output changes this guy. Changes this guy. And so on. And so I have to have at least that much connectiveness. Now, let's go back and look, for example, at the AND gate. Here we are back on this slide. Okay? And we can see some of these parts. For any particular AND gate, there is an A1, there is an A2 in the output. And those are an environment that was created those produce a frame. At the time AND gate was called, a frame where A1, A2, and output have as their values, they're bound to the wires which were passed in. In that environment, I constructed a procedure. This one, right there. AND action procedure was constructed in that environment. That was the result of evaluating a lambda expression. So it hangs onto the frame where these were defined. Part of its local state is that. Okay? The AND action procedure, therefore, has access to A1, A2, and output, as we see here. A1, A2, and output. Now, we haven't looked inside of a wire yet. That's all that remains. Well, let's look at a wire. Like the overhead. Very good. Well, the wire, again, is a somewhat complicated mess. Ooh, wrong one. Right? It's a big, complicated mess like that. But let's look at it in detail and see what's going on. Well, the wire is one of these. And it has to have two things that are part of it, its state. One of them is the signal we see here. In other words, when we call make wire to make a wire, then the first thing we do is we create some variables, which are the signal and the action procedures for this wire. in that context, we define various functions, or procedures, procedures. One of them is called set my signal to a new value. And what that does is takes a new value in. If that's equal to my current value of my signal, I'm done. Otherwise, I set the signal to the new value and call each of the action procedures that I've been what's the right word? That I've been introduced to. I get introduced when the AND gate was applied to me by add action procedure at the bottom. Also, I have to define a way of accepting an action procedure, which is what you see here, which increments my action procedures using set to the result of constantly up a new procedure, which is passed to me, onto my actions procedures list. And for technical reasons, I have to call that procedure once. I'm not going to tell you anything about that. That has to do with event-driven simulations and getting them started, okay, which takes a little bit of thinking. And finally, I'm going to define a thing called the dispatcher, which is a way of passing a message to a wire, which is going to be used to extract from it various information, like what is the current signal value? What is the method of setting your signal? I want to get that out of it. How do I add another action procedure? Okay. And I'm going to return that dispatch, that procedure, as a value. So the wire that I've constructed is a message accepting object which accepts message like what's your method of adding action procedures? That it'll give me a procedure, which is the add action procedure, which I can then apply to an action procedure to create another action procedure in the wire. Okay? So that's a permission. It says give me permission to change your action procedures. And in fact, you can see that over here. Next slide. This is nothing very interesting. The call each of the action procedures is just a cuttering down a list, and I'm not going to even talk about that anymore. We're too advanced for that. However, if I want to get a signal from a wire, I ask the wire, what is the wire? The wire is the dispatch returned by creating the wire. It's a procedure. I call that dispatch on the message get signal, and what I should expect to get is a method of getting a signal. Or actually, I get the signal. If I want to set a signal, okay, I want to change a signal, then what I'm going to do is take a wire as an argument and a new value for the signal. I'm going to ask the wire for permission to set its signal and use that permission, which is a procedure, on the new value. And if we go back to the overhead here, okay, thank you. If we go back to the overhead here, we see that if I ask for the method of setting the signal, that's over here. It's set my signal, a procedure that's defined inside the wire, which if we look over here, is the thing that says set my internal value called the signal, my internal variable, which is the signal, okay, to the new value, which is passed to me as an argument, and then call each of the action procedures, waking them up. Very simple. Okay, going back to that slide, we also have the one last thing, which I suppose now you can easily work out for yourself, is the way you add an action. You take a wire, and an action procedure, and I ask the wire for permission to add an action. Getting that permission, I use that permission to give it an action procedure. So that's a real object. There's a few more details about this. For example, how am I going to control this thing? How do I do these delays? Okay, let's look at that for a second. Next one here. Let's see. We know when we looked at the AND gate or the NOT gate that when a signal changed on the input, there was a delay. And then it was going to call a procedure which is going to change the output. Well, how are we going to do this? We're going to make up some mechanism, a fairly complicated mechanism at that, which we're going to have to be very careful about. But after a delay, we're going to do an action. A delay is a number, and an action is a procedure. What that's going to be is they're going to have a special structure called an agenda, which is a thing that organizes time and actions. I'm going to see that in a while. I don't want to get into that right now. But the agenda has a moment at which something happens. We're setting up for later, at some moment, which is the sum of the time, which is the delay time plus the current time that the agenda thinks things is now. Okay? We're going to set up to do this action and add that to the agenda. And the way this machine will now run is very simple. We have a thing called propagate, which is the way things run. If the agenda is empty, we're done, if there's nothing more to be done. Otherwise, we're going to take the first item off the agenda, and that's a procedure of no arguments. So that we can see extra parentheses here. We call that on no arguments. That takes the action. Then we remove that first item from the agenda, and we go around the propagation loop. So that's the overall structure of this thing. Now there's a few other things we can look at. And then we're going to look into the agenda a little while from now. May I have the overhead again? Well, in order to set this thing going, I just want to show you some behavior out of this simulator. By the way, you may think the simulator is very simple and probably too simple to be useful. The fact of the matter is that this simulator has been used to manufacture a fairly large computer. Okay, so this is a real live example. Actually, not exactly this simulator, because I'll tell you the difference. The difference is that there were many more different kinds of primitives. There was not just the word inverter or AND gate. There were things like edge-triggered flip-flops and latches, right? Transparent latches and adders and things like that. And the difficulty with that is that there's pages and pages of the definitions of all these primitives with numbers like LSO4. And then there's many more parameters of them it's not just one delay. There's things like setup times and hold times and all that. But with the exception of that part of the complexity, the structure of the simulator that we use for building a real computer that works is exactly what you're seeing here. Well, in any case, what we have here is a few simple things, like there's inverter delays being set up and making a new agenda. And then we can make some inputs, okay, and as input 1, input 2, a sum and a carry, which are wires. I'm going to put a special kind of object called a probe onto some of the wires, onto sum and onto carry. Okay? A probe is an object that has the property that when you change a wire it's attached to, it types out a message. It's an easy thing to do. And then once we have that, of course, when you put the probe on, the first thing it does, it says the current value of the sum at time 0 is 0. And because I've just noticed it. And the value of the carry at time 0, this is the time, is 0. And then we go off and we build some structure. Like we can build a structure here that says we have a half adder on input 1, input 2, sum and carry, and we're going to set the signal on input 1 to 1. We do some propagation. At time 8, which you could see going through this thing if you wanted to, the new value of sum became 1. And the thing says, I'm done. That wasn't very interesting. But we could set some more signals. Like we set signal on input 2 to be 1, and at that time if we propagate, then it carried at 11, the carry becomes 1, and at 16, the sum's new value becomes 0. And you might want to work out that if you like about the digital circuitry. It's true and it works, and it's not very interesting, but that's the kind of behavior we get out of this thing. So what I've shown you right now is a large-scale picture. How you, at a big scale, you implement an event-driven simulation of some sort, and how you might organize it to have nice hierarchical structure, allowing you to build abstract boxes that you can instantiate. But I haven't told you any of the details about how this agenda and things like that work. That we'll do next. And that's going to involve change and mutation of data and things like that. Are there any questions now before we go on? Thank you. Let's take a break.